First, I'd like to thank the organizers for inviting me to this fine meeting. It's the second time I've been here, and there have been some very interesting talks involving similarity measures, correlations, influence of variables upon other variables in very large, indeed massive sets of variables. And that's indeed what I'm going to talk about today. In a particular, we are concerned about quantifying uncertainty, like Alex Blocker in the previous talk, in doing correlation analysis for large data sets where you have replicated measurements. If you don't have replicated measurements, then of course you can't really talk about uncertainty without any additional prior information. If you have replicated measurements, you can start to explore the uncertainty that's associated with natural variability over the replicates of your correlation observations. The main point of this talk is that we can come up with systematic predictions of the number of replicates that are required in order to make particular inferences about influence among very large numbers of variables as measured by correlation and partial correlation, which I'll describe in a minute, when we focus on the problem of answering the question, what variables serve as hubs? Which variables tend to rise and fall with the rising tide of their neighbors? So either they're highly influential or highly influenceable by their neighbors. So I'm going to talk first about correlation networks and graphical models, because that's the approach we take to quantifying this uncertainty. And then I'm going to talk about screening for these hubs, which are just star graphs, subgraphs in a graphical model. Then I'm going to talk about how these can be applied to large-scale experiments so that you can right-size your experiment to achieve a given level of confidence on your correlations. So there's been a lot of reports in the recent press about the unreliability of scientific studies, industrial studies with large numbers of variables measured, where public confidence has perhaps been shaken somewhat by reports of putative correlations between seemingly unrelated variables. For example, a variable related to a woman eating cereal for breakfast and the variable related to her bearing a female child. This was actually published in a high-impact biological journal a few years ago, and the correlation existed, it's just that it was not reliable. So the model for our study is one which is a random matrix model. So we have samples, repeated samples of a number of p variables, and there are n of these samples. These get arranged into a matrix, n by p matrix, and we assume that these replicates of this p-variate massive variable vector are independent, identically distributed. And so the p by p covariance or dispersion matrix that's associated with each row of this measurement matrix is what we're going to be interested in. So there are two types of ways to deal with correlations in large numbers of variables. One is using the sparse structure of the correlations themselves to characterize those variables that are strongly related to each other and those that are not, and looking at degrees of separation, for example, between variables. And then there's also sparse inverse correlation models, which are also called concentration graphical models, or just graphical models for short, where one's interested in capturing relationships between variables that are conditionally independent as opposed to unconditionally or marginally independent. And examples of these two are, on the one hand, M-dependent processes, moving average processes, processes where there's really is only a finite dependency relationship between all the variables, and versus cases where there's actually dependency between all the variables or some large proportion, but there's this dependency is Markovian. So if you condition a pair of variables on the rest of the variables that are available, then those two variables may lose their putative dependence if you look just at the marginal correlation. So often only one of these domains is sparse. We're going to be concentrating on sparse inverse correlation because in the applications we've looked at, gene expression analysis and other applications, that's where sparsity seems to be the most apparent. So one way to understand the role of the inverse correlation as opposed to the correlation itself is through the multivariate Gaussian model. So if you assume that this matrix has rows, these p-variate rows, which obey this Gaussian model, where this is the density of each row, K is the inverse covariance matrix, and if K has zeros, say in the ijth place, it basically decouples xi and xj from this sum, giving you a multiplicative decomposition, a product decomposition of this joint probability into, say, two pieces if you have a Markovian dependency. And that means that the action is in the inverse covariance in terms of conditional dependency that has factorization properties of the multivariate distribution, as opposed to the structure that is the location of zeros in the covariance. So we draw a graphical model network, G, a graph, which has an edge if and only if the ijth element of this inverse covariance is equal to 0, in which case we draw an edge between the ijth variables. And then the adjacency matrix, of course, is extracted by thresholding or by looking at those entries that are not 0 in the inverse covariance. So here's an example, a very simple one, of a graphical model where the variables are actually related by a chain. So if you look at variable 5, it has correlation with all the other variables, 1 through 4, but conditioned on all of the variables 1, 2, 3, that it is uncorrelated of those if you condition on 4, right? So if you condition on 4, then 5 is independent of the rest. So this has a sparse inverse covariance structure, which is tridiagonal. Another example is the block diagonal case, where you have a graphical model that splits into two, cliques in this case. Another one is the conditional coupled block diagonal model, where condition on 3, these cliques 1 and 2 are independent. And then, of course, we have a tree model, which suggests additional structure, sparsity structure, in the graph, and as ensconced in the inverse correlation matrix or inverse covariance matrix. So what we're interested in this talk is looking at hubs in this graph that's formed from the correlation matrix. So the sparsity of the matrix induces a particular sparsity in the number of edges in the graph. And here I'm showing a particular variable in that graph with degree 1 through 5. And we're interested in discovering these from this finite set of measurements n measurements that I've mentioned before. So we can define the number of hub nodes of degree greater than d, or greater than or equal to d in this graphical model, simply by counting up the number of nodes that have that degree or more, right? And that's called n of d here. And the measurements, of course, deprive us of the ability to measure this directly. So we're going to have to estimate effectively this number. So there's a lot of previous work on the problem of inferring structure of graphical models. I'm not going to go into this background for lack of time, but suffice it to say that this work differs from the previous work in that, first of all, we're dealing with a testing problem as opposed to an estimation problem. We're not trying to estimate the inverse covariance. We're trying to test for structure, in this case, this hub structure, or sparse rows, if you like, in the matrix. And second of all, our theory is designed specifically for the practical case where you have a very small n and very large p, which we translate into a fixed n large p type of scenario. And we have unrestricted sparsity structure. All right, so we have to deal with estimating these, the sample covariance and the inverse sample covariance from n measurements. In this case, n is going to be less than p because n is fixed, p is very large. So we form the sample correlation matrix simply by normalizing all of the rows and columns of the sample covariance, which is sigma hat, which is familiar, I'm sure, to all of you, by subtracting the sample means and dividing by the sample standard deviation. We fill this matrix up. And that gives us the sample correlation coefficient, which is defined in this way, where this is the sample correlation between variables I and j divided by the product of their standard deviations. So critical to being able to build a theory for describing these fundamental limits on sample size, for being able to state with some degree of certainty that there actually is a hub in this graphical model, we transform our data into a sphered form of the data, basically by dividing through by sample deviation and subtracting the mean. We have what we call a z-score, and we can form then an equivalent z-score matrix, z1 through the zp, equivalent to the original measurements. And the z-score representation of R is basically an outer product. And this is critical because now we can talk about distances between these z-scores on the unit sphere of dimension n minus 2 due to these the removal of 2 degrees of freedom from this n-dimensional vector for each variable, and live now in this spherical geometry, which allows us to basically use geometric probability methods to characterize just how close two variables are on the sphere. The closer they are, the higher their sample correlation is going to be. So if you want to compute the probability that a given variable has no neighbors at some correlation threshold level rho, let's say, where rho is equal to the square root of 2 times 1 minus rho, and that's the radius here, then you basically construct this spherical cap with a center at the variable of interest, and you ask the question, you test the hypothesis that there are no other variables within that cap, right? Now, in this case, there are no variables, so this would not be a hub at this level of correlation. But say this one over here, this variable here, would have several other variables within its radius that I just mentioned. The relative surface area of the spherical cap plays a principal role here because that gives you the probability that if this was a random sample on the sphere, uniformly distributed, the probability that you might spuriously detect a hub, right? And this then is that probability, which involves the beta function and a corresponding integral. So this is evaluatable numerically, and it's a standard function. So for screening for hubs, we simply, in the partial correlation matrix, we simply need to compute an estimate of the partial correlation matrix from this sample correlation matrix. And so a solution with a question mark here, because this is actually not a solution, is to invert the sample correlation matrix and then normalize the rows and columns appropriately so that they have a magnitude 1 on the diagonal of this matrix. The problem is, of course, that when n is less than p, this inverse doesn't exist. So the solution that we put forward is to use a Moore-Penrose generalized inverse instead. And then second of all, false matches can occur at any threshold, of course, because of the fact that we only have a finite number of samples, so that there is some probability that within that little spherical cap you're going to get neighbors at any threshold level, any level of radius rho, even if you had no relation between the variables. So we're going to derive p-values for the false matches as the number of variables p gets large, and then finally their phase transitions. And so we give some mathematical theory in what I'll discuss in a few minutes that responds to these issues. So the projected z-scores is what we work with. I'm not going to talk about how we project the z-scores. We just remove a degree of freedom to account for the fact that we know that they're on a lower dimensional hyperplane by virtue of the fact that we have removed 1 degree of freedom by subtracting the mean. But this then becomes our pseudo-inverse partial correlation estimate. So if n is less than p, it turns out we have a outer product representation of this partial correlation matrix that is of the same form as the outer product representation that we had for the correlation matrix, which again means that we can look at properties of these z-scores, these derived z-scores y, on the unit sphere of dimension n minus 2 to describe the behavior of false positives and the formation of hubs in a graphical model using the partial correlation as opposed to the ordinary correlation. So now we use this quantity as our estimate for the number of hubs. We basically count the number of variables I for which there's another variable which is in radius square root of 2 times 1 minus rho of that particular variable. And that gives us an indicator function that we can sum up over from I equals 1 to p. And we're looking for delta of these for a degree delta hub. So that's the quantity of interest. And we have a theorem that I'm not going to, of course, try to prove to you here. But the theorem basically says that the variate that measures whether you have a hub of degree delta or not in your data among these potentially correlated variables behaves like a Poisson event. So the probability that we observe a hub is approximately equal to this Poisson-like probability where we have an intensity or rate function, lambda, that depends upon the hub degree that we're looking for and depends on the correlation threshold, the partial correlation threshold that we're using. And that intensity depends upon whether we're looking for simple connectedness of a variable to some other variable or connectedness in the sense of being a hub of degree greater than 1. We have an explicit form for this intensity, which is dependent on this spherical cap probability that I showed before. So this now gives us the ability to estimate the p-values. That is, estimate the probability that we observe hubs even though there are no hubs in the original model. And this formula applies whenever there are only a sparse number of hubs of this particular degree delta in the graphical model. So we can evaluate this false discovery probability, as we call it, that I just wrote before, as a function of the number of observations and a function of the applied threshold. And what we see is the phase transition phenomena that I mentioned a minute ago. So if we only have 10 variables versus 10,000 variables, the phase transition is much more putative for the larger number of variables. And this phase transition has a critical threshold rho c, which is the point at which we get this transition from probability 0 of false discoveries to probability 1 in this region that has this form here. So it decreases, rho c increases to 1 as p gets large at basically a rate which is of order p to the power 1 over n minus 2. We can look at this a little bit differently by looking at the probability of false positives for various numbers of variables. Here we go from 10 billion variables down to 10. And the remarkable thing is that if say we have 10,000 variables and only 100 observations, then if you look at the false discovery probability of discovering hub of degree 1 that is just connected, we're about that false discovery probability at 10%, then we can guarantee that probability if the correlation, the critical threshold, the correlation threshold is greater than 0.5. So that means that we can reliably detect true correlations greater than 0.5 with only 100 variables, 10,000 observations. Now, if you go to 10 billion observations, then you're over on this curve here, and it turns out that for the 6 orders of magnitude increase in the number of variables, we only have to increase the number of observations by a factor of 2 in order to get the same level of correlation discovery in terms of the discoverable correlation being greater than 0.5. So the theory tells us that actually the rate of growth of the number of required observations for any given performance operating level as a function of the number of variables is actually very slow, which is really good news, because it tells us that we can go up to a very large number of variables and still be able to ensure a false discovery probability, in this case of 10%, with reasonable range of discovery of true correlations. So I'm just going to conclude with a particular example of a 4-node graphical model. So this is a graphical model where if you condition on 2, 3 and 4 is independent of 1. That's why we have this kind of conditional block structure here. On the partial correlation, the correlation matrix for these 4 variables is full. It's not sparse. And what I'm going to add onto this is another 990 variables to make this 1,000 variables, but with the rest of them being independent. The partial correlation, again, is sparse up in this region where there's structure. If you compute the critical threshold for this 1,000-node network, you get about 0.7156. So that's what we would expect to be able to detect reliably at a 10% level. The critical threshold is 0.593, where we have that phase transition. But for a 10% false positive rate, this is the minimum detectable correlation magnitude that one would expect from this example. So if we set our threshold in that way, we can then be assured that any hubs that come up are going to be significant up to that particular level. So we can also describe a p-value, which again is the probability that the number of observed hubs of some degree k that have a correlation that's equal to the, in this case, the k-nearest neighbor distance of a particular variable I in our data gives us the probability of observing this event under the hypothesis that we're sparse. So this gives you a p-value that you can then plot all the p-values. We have 1,000 of them, and I'm just plotting the ones that are relatively small over here for hubs of degree 1 or more, hubs degree 2 or more, hubs degree 3 or more. And what we notice is that we have correctly picked up the node 2 as being highly significant. Well, not highly significant, because this only corresponds to about 12% in terms of the actual p-value, which is 1 minus e to the minus e log of lambda, which I'm plotting here on the vertical. But it's the most significant, if you like, within the rest of the variables. So hub 2, if you recall, is this hub right here, which indeed has degree 3. So here we're only making 40 observations. We have 1,000 variables. And yet we're able to discover with some significance, 12%, that 2 is a hub of degree 3. I terminate with a large-scale experiment where we looked at a breast cancer data set, Affymetrix human 133 gene chip, 295 samples now, 24,000 genes, and we're going to apply hub screening directly without any preprocessing to all of these gene probes. And the theory predicts that we'll be able to detect correlations that are greater than 0.296, which is quite a nice low number. If we fill this matrix up, this 24,000 by 295 matrix up with just white noise, just independent noise, this is what we get in terms of the p-values. They're all very low significance, right? These correspond to a significance of greater of less significant than 0.3 or 30 or 40%. So on the other hand, for the actual data, this is what we get. We get very high significance for certain genes as being hubs of degree 1. The C tag is a cancer transcription factor associated with breast cancer that came right out as being very highly significant as a hub of degree 1 or 2, so with a few neighbors, but it's not significant at all as a hub of degree greater than that. On the other hand, this interleukin gene is pretty significant for being a hub of low degree, but very significant for being a hub of high degree. So using this type of waterfall plot, as we call it, one can sort among the genes that have very high significance for being high degree or low degree or medium degree or not being significant at all. This just shows a plot of the previous study of this data using an algorithm called SPACE, which did have to pre-process using a Cox regression type of approach. And they get, they're also, all of their discoveries are on this curve. So we would also discover their particular genes at different hub degrees, but they're much less significant, if you noticed, than the ones that I showed you a minute ago. All right, so conclusion. We've introduced this large-scale hub screening method that allows you to decide where these critical thresholds are, how many samples you require in order to get a particular false discovery rate, and there are Poisson limits that basically give us these results so that you can describe mathematically the behavior of these critical thresholds. And we then have a couple of publications that you're welcome to take a look at if you're interested in more details on what I've just talked about. So with that, I will conclude my talk.
So what's the biological significance of those genes being hubs?
Yeah, so that's, of course, a question that one cannot answer without additional information about the pathways in which they lie. And so this is a discovery technique that applies irrespectively of any prior knowledge that you might have on common pathways or common linkages between different genes or functions of genes. So you can't answer that directly with this approach, which is one of the strengths, I think, of this approach, because it's not, let me say, influenced or biased by potentially, unreliable data, like the example I gave in the beginning of the talk. But on the other hand, once you've done this, you've pulled out these p-values. They can only be larger, more significant, if there are pathways that connect these genes together. Right? So you have to follow up with a post-analysis, in other words. Yeah, excellent question. So the question is, to what extent does the elliptically contoured assumption on the distribution of the variables influence our results? And did we check to see whether or not the elliptical assumptions were verified? So the answer to the first question is that they affect these results only in the form of the intensities of the Poisson limits. So it turns out the Poisson limits hold under a much broader assumption. In fact, all you really need is that the joint density be bounded and smooth. But what the problem is that you now lose this universality property where sparsity in the dispersion matrix is sufficient to give you a distribution-independent rate function, right? So you can't derive these p-values unless you truly believe that you have elliptical distribution. If you have another family that's not elliptical, you could make that assumption and then have p-values under that set of that class also. In terms of validating the ellipticity assumption, we have done some of that. It's one of the active areas of research now is to try and relax that assumption. But in the data that we've observed, the ellipticity seems to be pretty well validated. So in the gene expression data, when you have so many variables, unless you have clusters, right, which are very well defined, then the ellipticity assumption is actually pretty good. I think it's when you get into cases where you have relatively few variables and you lack this mixing of all the variables that you lose this ellipticity. There is a paper that was published by our group, Kumar Sricharan, who actually I should acknowledge here for his role in this research, who's sitting in the front row working at NASA Ames now. He published a paper which studied the effect of this ellipticity assumption on the intensity, the universality of these rate functions relative to the null hypothesis.
Thank you. Thank you.